Hello everyone, I'm Jiayue. Welcome to my channel. Today let's talk about spin. So in the last videos, we were talking about the Dirac equation and the gamma matrices. So now first let's review that. For the most important thing we know is the Clifford algebra, which is just the anti-commutator of gamma nu equals to 2 eta mu nu, and I here are some identity matrices, and we say it is 4 by 4 identity, and we also know that the generators of Lorentz group J mu nu equals to I minus 4, and the commutator of gamma nu. So today let's play with these two things. First, we need to find a set of gamma matrices that satisfy this Clifford algebra, and if we find the set, it is called a representation. Let's talk about the most important, most popular representation called Chiral representation or Weyl representation, which is we have this set of gamma matrices. We have gamma 0 equals to I here are just a 2 by 2 matrix, and so the whole thing is 4 by 4 matrix. And then we have gamma I equals to sigma I minus sigma I. Here are just some 0, but I didn't write this 0 for simplicity. Okay. Now here sigma I are Pauli matrices. We have sigma 1 equals to 1, 1, sigma 2 equals to minus I, sigma 3 equals to 1 minus 1. So you can simply verify that if I give you this set of gamma matrices, it can satisfy this Clifford algebra, so it is a good choice. So let's start with this choice. Let's start with this Weyl representation. So we have the Pauli matrices here, and if we know these things, we can compute the generator of the Lorentz group J mu nu. So what is J mu nu? J mu nu is just this thing, and we shall think of a question: what is spin? What is spin? It is related to any rotation. We don't know that, but we shall learn something from the generators of the Lorentz group. First, let's study J12. For example, if I compute the Ji2, for Ji2, you can think of it as some rotation around the z-axis. So let's plug in the gamma matrices I given here. Gamma 1 is just sigma 1 minus sigma 1, and sigma 2 minus sigma 2, and minus gamma 2 times gamma 1, which is sigma 2 minus sigma 2, sigma 1 minus sigma 1. And here we get this is a new matrix, which is the first element is minus sigma 1, sigma 2, and this 0, 0, and the last thing is this times this, so it's still minus sigma 1, sigma 2, minus this thing. This is minus sigma 2, sigma 1, and here is also minus sigma 2, sigma 1, and this empty space adjust zeros. So we want to know sigma 1, sigma 2, and sigma 2, sigma 1. We compute the matrix multiplication of the gamma matrices here. So what is sigma 1, sigma 2? Sigma 1, sigma 2, adjust this times this, so it becomes the first element is I, and this element is minus I. So it is just sigma 3, right? So it is I sigma 3, and sigma 2, sigma 1 is this times this. So the first element is this times this, so it's minus I. So it's just minus I sigma 3, right? So we plug in this into here, so we get minus sigma 1, sigma 2 is just minus I sigma 3. Minus I sigma 3, minus I sigma 3, minus sigma 2, sigma I is I sigma 3. So this is I sigma 3. It's still I sigma 3. So we get 2I sigma 3. 2I sigma 3. Sigma 3. So this is our result. And we can cancel this minus 2I here with this coefficient. So it becomes minus a half sigma 3, sigma 3. So this is our final result. So usually the angular momentum of around z-axis is defined as minus J12. So it is because we choose our signature as 1 plus and 3 minus sign. So for a rotation transformation, or say this in this representation, the Lorentz group is, let's talk about the rotation around the z-axis. It is, so it becomes I theta over 2 and sigma 3, sigma 3. And the minus sign was cancelled here. So this is our final result for the rotational matrix. And if we look at the rotational matrix, what shall we find? Let's see some specific examples. Like, what if I rotate 2 pi? Let's see that. If I rotate 2 pi, so it becomes theta over 2 is pi, so it becomes E I pi, and sigma 3 here are just 1 and minus 1, and you can see no matter it is 1 or minus 1, it is just I mean for for each one, either it is e to the I pi or it is e to the minus I pi, but e to the I pi or e to the minus I pi, they are all minus 1, right? So it's minus identity. So if I rotate 2 pi, I cannot get back to myself. What? So it's a little bit strange, right? So how can I get back to myself? How about if I rotate 4 pi? If I rotate 4 pi, it becomes I2 pi. And e to the I2 pi or e to the minus I2 pi is always 1. So I get back to myself. And what is spin? Definition of a spin is that an object with spin x can get back to itself when it rotates 2 pi over x. So a spin x object can get back to itself, after 2 pi over x rotation. So this is our definition of a spin. So for this case, I can rotate 4 pi to get back to myself. So how can we get 4 pi here? 4 pi is 2 pi over 1/2. 4 pi is 2 pi over half. So our spin is a half. So our spin x here is just a half. So for this representation, it is a spinor representation and has a spin a half. So this is our final result. We can see that after this simple calculations, we can find the motivation of the spin. Isn't it cool? That's all. Thank you.